Hardness basics. Hardness is the ability of a material to resist indentation or localized deformation. It's commonly tested using nondestructive methods, primarily in laboratories rather than in the field. Hardness testing is a crucial tool for quality control, ensuring that materials meet specific strength and durability requirements. In welding, hardness tests help assess the properties of the weld metal. By carefully analyzing a welded joint, we can identify hard zones and determine how welding heat has affected the base metal's properties. Hardness versus tensile strength. This graph illustrates the relationship between hardness and tensile strength in carbon steels. In steel, hardness and tensile strength are directly correlated, meaning that as hardness increases, so does the material's ability to withstand pulling forces before breaking. This relationship is often considered linear, allowing us to estimate tensile strength based on measured hardness values using empirical equations. Hardness versus tensile strength. This graph illustrates the relationship between hardness and tensile strength in carbon steels. In steel, hardness and tensile strength are directly correlated, meaning that as hardness increases, so does the material's ability to withstand pulling forces before breaking. This relationship is often considered linear, allowing us to estimate tensile strength based on measured hardness values using empirical equations. Okay, I know you hated chemistry, but we need to talk about carbon in steel. Carbon is the element that gives steel its edge. It's what makes steel harder, stronger, and capable of withstanding higher forces. But here's the catch. Too much carbon comes with trade-offs. Let's break it down so you can actually use this info where it matters. What carbon adds to steel. As we increase carbon content in steel, here's what happens. Increases hardness, tensile strength, brittleness, and yield strength. Downside, it rusts faster and becomes harder to work with. So a little carbon makes steel tougher, but a lot? That's a whole different beast. The drawbacks of high carbon. More carbon also means we lose some key qualities. Decreases weldability above 0.25% carbon, welding gets tricky, plasticity, ductility, and corrosion resistance. The kicker, high carbon steel gets brittle, which means it can crack if it's not handled just right. Welding high carbon steel. If you're welding steel with a high carbon content, you've got to plan ahead. More carbon equals more preheat and post-weld heat treatment. Why? Because you're fighting brittleness and trying to keep those welds from cracking. Skip these steps and you'll be dealing with defects faster than you can strike an arc. Here's the bottom line. Carbon is like seasoning. Too little, and steel's soft and weak. Too much, and it's brittle and hard to weld. For most structural steels, we stick to under 0.3% carbon to keep weldability and ductility. But for tool steels, you're cranking up the carbon for extra strength. And that's a whole different game.